Hello everyone. So in this video, we're going to talk about something called an LU factorization. An LU factorization is a way of taking a matrix A and splitting it, factoring it, as the name would suggest. Specifically, LU factorization is the process of taking a matrix A and rewriting it as a product of two matrices. One matrix L, which is lower triangular, and one matrix U, which is upper triangular. So LU factorization factors or splits a matrix into a lower triangular part and an upper triangular part. The purpose of LU factorization, that can make matrix equations involving A easier in some sense to solve. To give you an example of that, suppose that we have a matrix A and its LU factorization has the lower triangular part 1, 0, 0, 2, 1, 0, 1, 3, 1, and an upper triangular part 1, 1, minus 1, 0, 2, 4, and 0, 0, 1. Using this LU factorization, let's go ahead and solve this matrix equation involving A. A times x needs to equal 1, 4, 3, that vector. So given that A is equal to L times U, the first thing that I'm going to do in this matrix equation is replace the A with L times U. So this is the matrix equation I'm trying to solve. If I call B this vector 1, 4, 3 that I'm trying to output. I'm going to go ahead and I'm going to solve this equation in two steps. I'm going to start, for example, by calling this result ux equal to a vector y. And I'm going to consider the equation L times y equals b. I'm going to start by solving this equation for the vector y, and then I will, in a secondary step, solve this equation for the vector x. The reason I'm going to do this is because, as we said at the end of our determinants video, we noted that when you solve equations involving lower triangular matrices and upper triangular matrices, that process is usually pretty quick because you can usually get one of the entries of the solution just by reading one of the rows, and then you can find the other entries just by substitution. So let's see that in action again here. Take the matrix L. I want to multiply that matrix by the vector y and output this vector 1, 4, 3. So if I read these rows for information about the entries of our y vector, the first row is going to say that y1 must be equal to 1. And then from the second row, I get the statement 2y1 plus y2 equals 4. And just by substitution, I can get the value of y2 very quickly. Then reading the third row of this matrix equation, I get y1 plus 3y2 plus y3 equals 3. And if I substitute in the values of y1 and y2, which we found earlier, I get 1 plus 2 times 3 plus y3 equals 3, and that forces y3 to be equal to negative 4. So I found the entries of the vector y. The vector y has entries of 1, 2, and minus 4. Now I will remind myself that ux was what I said was going to be equal to y. So I will go ahead and put back ux in y's position. And I'll try and solve this equation for the vector x that I was looking for in my original matrix equation. Once again, because I'm dealing here with a triangular matrix, it has in some sense already been row reduced. So I can find the answers just by reading the rows and doing some substitution. That bottom row tells me immediately that x3 is equal to negative 4. In the second row, 2x2 plus 4x3 equals 2. I substitute in. I get 2x2 plus 4 times negative 4 equals 2. So 2x2 equals 18. So x2 is equal to 9 by my reckoning. Then read the top row that says x1 plus x2 minus x3 must equal 1 on the far side. If I substitute in the x1 and the x2 that I found earlier, I get negative 4 plus 9 minus x3 is equal to 1. So that is negative x3 subtract 4 equals minus 4, x3 equals 4 by my reckoning. So via this two-step solving process, we've gotten our solutions. X equals negative 4, 9, and 4. If your A has been factored in this format, you can solve matrix equations involving A really just by doing a lot of substitution. So now let's talk about how the LU factorization of a matrix is found if it's not given to you at the start of the problem. So here's the full step-by-step process. We'll go through these steps one by one as we work through a demonstration using this matrix A given here below, 1, 1, 1, 4, 3, minus 1, 3, 5, 3. So step number one of constructing an LU factorization for a matrix. You start out by writing down a lower triangular matrix L, and you set up the matrix L in sort of a template format. First of all, how large should L be? The size of your lower triangular matrix L, it should be a square matrix with the same number of rows as A. So if I take that step into this demonstration, my matrix A has 3 rows. So the matrix L is going to be 3 by 3, a square matrix with the same number of rows as A. Now, as we set up our template for the matrix L, let's remember that it is going to be lower triangular, which means all the entries above the diagonal are going to be 0 for sure. So then it's just a question of what's going to be on the diagonal and what's going to be underneath the diagonal. Now, when we set up our template matrix L, we always agree to have ones on the main diagonal. So you can also fill that in immediately as well. We're going to, in the algorithm, have ones on the main diagonal. So then the question just remains, if we have zeros above the diagonal, and if we have ones on the diagonal, what entries are going to go below the diagonal? So to answer that question, we're going to move to step 2 of the factorization algorithm. You're going to take your matrix A and you're going to begin to convert it to row echelon form. Not reduced row echelon form. You're not going to do Gauss-Jordan elimination. You're going to do Gaussian elimination, just going through that forward elimination process. But here's the catch. As you are converting A to row echelon form, you're not allowed to swap rows, and you're not allowed to scale rows either. The only operation that you're allowed to perform is the one that we called row replacement. You are only allowed to perform this action of adding some number of row whatever added to whatever other row. This is the only action that you are allowed to perform while row reducing A in the LU factorization algorithm. So let's go ahead and perform that action on this matrix A. Let's go ahead and write this matrix A in row echelon form. Let's eliminate these values underneath the diagonal, underneath the pivot positions, using only this action of adding copies of one row to another. So to that end, the first thing that I would do to the matrix A, the first thing that I would do is I would add -4 copies of row 1 to the second row. I would do this because that would allow me to eliminate the value of 4 underneath the diagonal of the matrix A. And so that action would bring me to this situation right here, 1, 1, 1, and then 0. And then -4 times 1 plus 3 is -1. -4 times 1 plus -1 is -5. Now, having performed that action on the matrix A, I'm going to fill in one of the blanks in my template matrix L. I'm going to take this number that I used in my row replacement operation, this number -4, and I'm going to put its negative +4 in this position here in the second row. Continuing to work on row reducing the matrix A, the next thing that I would do is I would add -3 copies of row number 1 to row number 3. I would do that to eliminate the 3 in this third position here. 1, 1, 1, 0, -1, -5, and then 0, and then 2, and then 0 again. Having done that operation, I'm now going to take this value of -3, which I used in this row elimination process, and I'm going to place the opposite of that, +3, inside of L. Finally, I would act to eliminate this value underneath -1 in the third row of A. So the next thing that I would do is I would add 2 copies of row number 2 into row number 3. Remember that the only operation we are permitted to perform here is row replacement. So I would not be permitted in this algorithm to swap these two rows. I would not be permitted to scale this row. I'm only allowed to try and add this row down into the third row. And if I perform that action on the matrix A, that now brings me to A tilde being equal to 1, 1, 1, 0, -1, -5, and then 0, and then 0, and then -10. So having added 2 copies of row number 2 into the third row, I would then take that value of 2 that I used in that step, I would take that value of 2 and I would use its opposite to plug in to this position. Here, using a scalar of -3, I put in a +3. Here, having used a scalar multiple of -4, we put in a +4. And here, having used a scalar of 2, we have put in here a -2. So always, whatever scalar you use in the row replacement action, the opposite of that scalar is going to go in the appropriate position in your L matrix. Now notice that as of this moment, L is completely filled in. And also notice that as of this moment, this matrix A has been converted to something that is upper triangular. So with this step, we have both finished finding the matrix L and we've finished finding the matrix U, because this matrix in upper triangular form, this is the matrix U in the LU factorization. So A is equal to the lower triangular matrix L that we found was 4, 3, -2 in the bottom left corner. And the matrix U is this 1, 1, 1, 0, -1, -5, and 0, 0, -10. This is the LU factorization of the matrix A. To do it, row reduce the matrix A while keeping track of the scalars that you use in the row replacement operations. Those scalars fill in the blanks of the lower triangular matrix, and then the result of the row reduction is the upper triangular matrix in the factored form. So let's talk now a little bit about why this algorithm works to produce the matrix L and the matrix U such that L times U is equal to A. Let's talk about why this works. And to that end, I'm going to return to what we learned in the previous lesson about elementary matrices. We remember that every single one of the actions that we performed in this row reduction process can be represented by an elementary matrix. For example, let me call this first step, step number 1. In step number 1, we performed the action of adding negative 4 copies of row number 1 to row number 2. This action, represented as an elementary matrix, would be to do that same operation to the identity and push a negative 4 into this position in row 2, column 1. The second operation, likewise, where we've added negative 3 copies of the first row into the third row. This operation can be represented by a second elementary matrix where we perform that same action on the identity. So that would put a value of negative 3 in the third row in the first column. And then this third step as well, this third step of adding 2 copies of row number 2 into row number 3, that third step can also be represented using a third elementary matrix, which has that value of 2 in the third row and the second column. Now, in this algorithm, we have performed these 3 actions on the matrix A back to back. We took the matrix A and we first applied the elementary row operation number 1. So that would correspond to left multiplying by the matrix E1. After that, we multiplied by the matrix E2. That would correspond to performing the second step of the row reduction process. And after that, we performed the third step of the row reduction process, which would correspond to multiplying again by the matrix E3. And by performing these 3 elementary row operations, one after another, that transformed the matrix A into the upper triangular matrix U. So now let me go into this equation and let me solve this equation for A. And let me rearrange this equation and rewrite it with A isolated. And to that end, I'm going to try and move these elementary matrices over to the other side of this equation. I'm going to try and do that by applying the inverse of these matrices to both sides of the equation. For example, if I apply E3 inverse to both sides of this equation, to the U on the left and to the E3, E2, E1 times A on the right, if I do that, that's going to cancel out the E3 on the right side of this equation, and that'll eliminate part of what's going on over here next to A. Similarly, I can apply E2 inverse on both sides of the equation. And if I apply E2 inverse on both sides of the equation, that's going to cancel the E2 that's currently on the right. And finally, I can eliminate the E1 from both sides of the equation. Apply E1 inverse to both sides of the equation, and that will cancel out that final elementary matrix, and it will leave A all by itself on the right-hand side. So what we've said is that for the elementary matrices that we've constructed by doing these three elementary row operations, we've expressed A as a product of these three elementary matrices, E1 inverse, E2 inverse, E3 inverse, and that guy times U. My claim is that this product of these three elementary matrices is what has become the matrix L that we constructed during this algorithm. And to prove that, let's think about what the inverses of these elementary matrices would be and what would happen when we multiply them all together. Remember in the previous lesson, we said that inverses of elementary matrices are pretty easy to find. If you want to find the inverse of an elementary matrix, you just have to perform the action of the original matrix in reverse. So if the original matrix added -4 copies of row 1 into row 2, the inverse would just add +4 copies of row 1 into row 2. So that's how, although we used -4 in our row reduction process, our matrix over here on the side ends up with a +4 in that position. +4 because we're dealing with the inverse action, the inverse of this elementary matrix. Similarly, the inverse of E2 is 1's on the diagonal, 0's above, but that -3 has changed to its opposite, to the number +3. And similarly, E3 inverse is equal to 1, 0, 0, 0, 1, 0, 0 minus 2, 1. -2 in that position because this is the inverse of E3, meant to perform the opposite action as E3. So now if I multiply all those inverse matrices together, if you go through with this matrix product and you do those calculations, you can confirm that those three matrices multiplied together result in exactly the matrix L that we found earlier using the given algorithm. So that's a little bit about why this algorithm works and why this particular process is used to find the matrix L. The matrix L contains these entries in the bottom left corner, formed by taking the opposites of these scalars in the row replacement. Opposites because these values are coming from the inverses of the elementary matrices representing the steps that we took. So that's the LU factorization process. LU factorization is the process of taking a matrix A and splitting it into two parts, a lower triangular matrix L and an upper triangular matrix U. If your matrix A has been split in this fashion, it allows you to solve matrix equations involving A without doing any additional row reduction, just by essentially using lots and lots of substitution. The LU factorization of a matrix can be found by doing forward elimination on A, doing Gaussian elimination on A, but a restricted type of Gaussian elimination, where you're not allowed to swap rows and you're not allowed to scale rows. You're only allowed to add copies of one row to another. As you perform those row replacement operations, you need to track the scalars that you're using in every step because the opposites of those scalars are what is going to form the entries of the matrix L. And then after A has been row reduced, the result is equal to the upper triangular matrix U. And we talked a little bit about why that is. To note, if it's not possible to row reduce A without doing any row swapping, then A cannot be written in LU factored form. If you cannot get A into row echelon form without swapping rows, then A does not have an LU factorization. So to close out this video, let's just discuss the three different approaches to solving AX equals B that we have established up to this point. We've established just the regular row reduction method. Just set up your augmented matrix A augmented with B, row reduce that, and read the solutions. sort of on the far end of the extreme is to invert the matrix A and then um, get X by doing A inverse times B. And sort of middle ground here is to factor A as L times U, then solve Ly equals B, and then solve Ux equals Y. The three different means that we, in theory, could use to solve any given matrix equation. To discuss the pros and cons of these three options, I think regular row reduction is certainly the most reliable. No matter what is going on with your matrix A, you will be able to say something intelligent about the solutions to this equation. So this is the most reliable method that works on the largest number of different matrices A. And this is particularly well suited if you're only using the matrix A once, if you're only solving one equation involving the matrix A. Whereas these other two methods, once again, are most suitable if you're in a situation where the same matrix A is appearing in multiple different equations and in multiple different problems. Then inverting the matrix A or factoring the matrix A can be considered an upfront investment. An upfront investment that allows you to transform A into a form that makes the subsequent calculations faster and easier. But the downside of these other methods is that not only are they slow for a sort of one-off or one-shot problem, it's also not possible to use these other two methods in certain situations. If you cannot row reduce your matrix A without swapping rows, then the LU factorization might not even exist. Likewise, if you're dealing with a singular matrix A inverse might not exist. In order for A inverse to exist, not only does A have to be invertible, but A in particular has to be square. Whereas by contrast, LU factorization works on matrices that are both square and rectangular. So here is a layout of sort of the pros and cons of these three methods.